This is the world's leading telescope, the Keck Observatory in Hawaii. But it wouldn't exist without a series of engineering connections. The incredible ideas and inventions hidden deep within its design. A legendary ancient death ray.
There we go. There it's burning.
An industrial sandblaster. A strange musical instrument. A Cold War spy plane. And the secret of the refrigerator.
Oh, burst it! How do you put these together to see further into space than anyone has ever managed before?
I'm on a journey to reveal the engineering triumphs embedded in the Keck Space Observatory in Hawaii. This is tropical Hawaii. It's cold because this particular point is almost 4,000 meters above sea level. More important than the temperature, that means the air is thin. And that is why those are here. A dozen observatories perch on the summit of Mauna Kea. It's a dormant volcano. And it better be, because $600 million have been spent building the observatories up here.
I don't know. Maybe it's my overactive imagination, but sometimes it's as strange and alien up here as the places these telescopes were designed to study.
At this altitude, it's hard to breathe. But Mauna Kea's thin air and isolated position reduce atmospheric distortion, making it perfect for astronomy. It's why there are so many different observatories on the summit. Among them, the world's most important, the Keck telescopes. Telescopes magnify images, which are made of light.
At the heart of every telescope is one of these. Well, not actually one of these, obviously, but a device for focusing light.
The common or garden solution is to use a glass lens, which focuses a faraway image, as in the Yerkes Observatory in Wisconsin. Looking through the telescope's eyepiece, we see a big image. A lens is like a bucket. The bigger it is, the more light it collects and focuses, and the bigger and more detailed the image. To see deep into the universe, astronomers want big lenses. In 1896, scientists construct the world's largest glass lens for Yerkes. It's just over 1 meter wide. But making glass lenses is notoriously difficult. It takes 19 attempts over 3 years just to produce the glass for a lens similar in size to Yerkes. And that's before grinding and polishing. 100 years later, Keck's designers need a lens 100 times bigger than Yerkes to see the deepest recesses of space. They need a lens 10 meters wide. But astronomers abandoned large glass lenses as the way forward. Keck's engineers need a different way of collecting a huge quantity of light. Their method for creating a revolutionary new lens takes them on a journey back over 2,000 years to one of the world's first scientists, Archimedes, and his legendary ancient death ray. Down at sea level, Keck engineer Craig Nance reveals more about this ancient device.
Well, you can take a large mirror that has a concave shape to it, and the sunlight falls on the mirror and comes to a focus, and it's a very intense, bright spot. Perhaps you've heard of the legend of Archimedes?
Wasn't he the guy who shouted Eureka when he got in the bath?
Yes, that's right.
We've all done it.
That's right. Well, he also used these large reflecting mirrors, the legend says, to set fire to a Roman fleet that was attacking his city.
What, he set fire to them with a big reflector?
That's right, that's what the legend says. So, would you like to try it?
Yes.
Well, let's come on, let's go.
All right.
To test the story of Archimedes' death ray, we're going to need 3 things: sunshine and 2 items from Craig's little convoy.
Should I ask what this is?
It's not a Roman galley, but it's made of wood, so the principle will be the same.
Very nice.
Next up, the death ray itself.
Wow! That looks suspiciously like a mirror.
It's shaped just like a satellite dish, probably because it is a satellite dish, curved to focus the signal to a point, in this case, the sun's rays. We're testing this on an old airstrip under the watchful gaze of the local volunteer firefighters.
Set this up on the horses. Just put a nice X there.
Hey, look, that's the target.
And we're gonna aim right for the middle of that.
Okay.
And it's gonna take you and I both to hold this mirror.
Local engineer Weldon Sheldon is our modern-day Archimedes.
Very optimistic.
Okay, we wanna bring this in.
So we can see how it's bringing the light in, it's focusing it up
Yeah.
on the mark.
Even with Hawaii's hot sunshine, I'm not sure this is going to work.
You see, I'm starting to see a little dark spot on there.
I was wondering if that was just my eyes.
No, that's not your eyes. It's actually,
The smoke. It is catching. That's just because we're focusing all of the light that's hitting your satellite dish covered in aluminium foil.
I saw flames for a moment there. Did you see that?
Yeah.
There we go. There it's burning.
Look at the fire guys. They get all twitchy. Wait. This is science going on. Don't interrupt it. Let's just remind ourselves, what we're talking about here is focusing light. We're concentrating all of the light that's hitting this big dish onto that one little spot there, and all that light in one place means a lot of energy.
That's right, it does.
And a burnt boat.
Taking off.
So look, it really does turn out then Archimedes quite possibly could have set fire to that fleet with a mirror.
Yeah, could possibly. Well,
The only thing is, he wouldn't have wanted to stand this close because they'd have been
That's
quite
right.
cross and they'd have stabbed him by now.
That's right.
And also it'd have been wet. But the larger the mirror, the more light you're catching and focusing.
That's right. The larger the mirror, the more light you're concentrating.
I think we've proved the point.
Yeah.
Guys, there's a fire. And we've made a... Yeah, sorry.
Archimedes' death ray proves that a curved mirror can concentrate and focus light in the exact same way as a glass lens. For astronomers, it's a revolutionary idea. In 1668, Isaac Newton builds a new kind of telescope. It still has an eyepiece, but instead of a glass lens, a curved mirror not even 4 centimeters wide focuses the light. Fast forward 325 years to the Keck Observatory and to a mirror that focuses 70,000 times more light. This is it. 10 meters wide, it does the exact same job as a glass lens, but a lot more cheaply. At just $36 million, it's a steal. In fact, Keck has a series of mirrors to focus light. The huge primary mirror collects the beams, bounces them to a smaller second one, and then to a third, which reflects them to a camera, which replaces the old-fashioned eyepiece and records images of the cosmos in unprecedented detail. The mirrors are all housed in a support 8 stories high, weighing 275 tons. And yet the device can operate with nanometer precision. And the Keck Observatory has 2 of these intricate arrays that work together. As astronomer Sri Kulkarni explains.
Bigger the mirror, the better. Now think of these 2 telescopes as 2 ends of a mirror.
Even though there's a 75-meter gap between Keck 1 and Keck 2, they work just like one big telescope, with a huge mirror 85 meters wide.
The quality of image we get is 8 times better than what we can do with a single telescope.
But designing the world's biggest telescope mirrors is one thing. Building them is another. Nobody has ever constructed a mirror this big before. So just how did Keck's engineers do it? And shape it into the exact right curve? And how does a weird-sounding musical instrument provide the answer? In astronomy, there's a simple rule. Biggest is best. That's why the designers of the Keck Observatory want to create what is going to be the world's largest telescope mirror to see further into space than ever before. But making a mirror 10 meters wide presents them with a mighty problem if they try to construct it from a single piece of glass. Rewind to 1948. The California Institute of Technology builds the Hale telescope. It houses what is then the world's largest glass mirror, seen here with engineers preparing to apply a new reflective coating. Just over 5 meters wide, astronomers believe they have reached their limits with a single mirror. Nature seemed to have decided how big a mirror could be. This is a piece of plastic, similar properties to glass, and it's pretty sturdy, but triple its size, and suddenly, well, it sags in the middle. It hasn't got sufficient strength to hold itself up. The only way to make it stronger at this size would be to make it thicker, but then it would be heavier, and you need a lot more to support it. It's a vicious circle. The larger the glass, the heavier it is, and to brace it against gravity, it needs support and reinforcement, which only makes it heavier and increasingly expensive. Just over 5 meters seems to be as big as astronomers can go. But Keck's engineers need a mirror almost 4 times as big. So they come up with a pioneering design that transforms astronomy. Instead of creating a single huge mirror, they use 36 hexagonal segments that fit together. But making a big mirror out of little ones creates a new problem. You need to arrange each segment so it lines up exactly with its neighbors and makes a smooth, continuous surface. If it doesn't, the mirror won't make the perfect curve to focus the light accurately. The solution lies in a weird-sounding musical instrument called the theremin. In 1919, Leon Theremin, a Russian inventor, experiments to create a sensor for an alarm system. He ends up creating a musical instrument. Tom Bach of Sensitech Research, an expert in electric field sensors, shows me the instrument. Okay, Tom, talk me through it. It's making a noise already. What is it? What does it do?
Well, this object measures the changes of electric field. As you bring your hand in, we're distorting the electric field that's been created around that rod.
So hang on, I'm going to play this now. It's like
That's right.
theremin.
That's right.
And it's like an instrument, and I don't touch it. I just get
No.
What? Well, it's very, very clever. But is it of any use whatsoever?
Oh, yes. It will measure the presence of anything that will distort that field. It doesn't have to be a metal object. It can be a gas or a chemical or the human body moving in and out, or you can put it in an engine. You can measure how fast the engine's going. You could even theoretically, by turning that magnification up, you could watch the moon go over. Well, not done it though.
It can tell you when the moon goes over.
Well, yeah, no, that's an idea. A lot of these things are theoretical, but you could, yeah, theoretically, it'd be fun to try that.
And it's very sensitive because a tiny movement makes a tiny difference.
Yeah, it does. Yeah, that does.
It seems there's almost no limit to what these sensors can detect. To prove it, Tom devises a little test for me, finding a needle in a haystack. Well, one slightly different tennis ball out of 500. While my back is turned, Tom injects a little bit of water into a tennis ball. Theremin-type sensors detect the tiniest disturbance to the electric fields around them. It can be hands waving about, or just a little bit of liquid that makes one ball conduct electricity slightly differently, so it will clearly stand out among the 500 other balls. Tom sets me to find the doctored ball. First of all, without a sensor.
And I can give you too much help here. You've got to
so
find.
it's just some invisible difference.
Yep. I mean, there's only 500 of them here, so that shouldn't be hard. You got to try. You got to really try. You know?
Are they different weights? Are they? Oh, well, that would take days. I can't pick every one up.
If I could detect changes in electrical fields, finding it would be a walk in the park.
Clearly, I'm not going to find it.
Okay, well, we made you something that's an electric field sensor, so it will find changes in the electric field. So you should be able to use this to find it.
So this works.
Yep.
I'm guessing the same as.
But a bit like the theremin, but it's a more.
So I just search.
More sensitive. Yeah.
All right.
Intuition, logic.
Are all useless.
All useless, I think, too.
It's just that noise that I'm waiting for. Hang on.
Got it.
Is that it?
Yeah, it's got it.
I've got it, and it's just that difference compared to an ordinary one.
That's right.
It doesn't feel any different, it doesn't look any different.
No. Good.
That's one sensitive machine.
So how do the sensors used in a weird musical instrument help the Keck astronomers build their enormous mirror out of 36 segments? For the answer, Keck engineer Craig Nance shows me one of the pieces of the jigsaw.
Here's one of the Keck segments.
So that is one of the segments that makes up the whole mirror then?
That's correct. So each segment has to have the unique part of the overall curve. So each segment is a portion of the curve, and then the next segment picks up the continuation of that curve, so that the entire 36 mirrors all create one beautifully mosaicked.
So that all together, added together, you've got that constant curve around the whole thing.
That's correct.
Sounds simple, but to make the exact right shape, the astronomers must ensure each curved segment lines up perfectly with its neighbour. Where two segments meet, the edges have to make a continuous smooth surface without any steps. If one edge is a tiny bit too high, the mirror won't function. That's where the theremin comes in. Engineers use theremin-type sensors to measure the electrical fields wherever two segments meet. The sensors are so sensitive, they will detect a misalignment of just nanometers. Much in the same way, I was able to spot the tennis ball with a tiny bit of water in it.
This is one of the segments that we've removed that front surface aluminum coating so you can see all of what's going on behind the glass.
So all of this machinery then is constantly measuring and adjusting where this particular mirror is in relation to the rest of them.
That's right. About twice per second, these sensors are being used to figure out where the segment is located and then command it as needed to adjust so that the entire array of mirrors maintains that wonderful optical shape that we need.
And let me guess, the movements, the adjustments are kind of small and precise.
That's right, they are. The optical tolerances we're looking at are about 1/1000th of the thickness of a human hair.
Well, so you've got to position it
That's
to
right.
within... And this
That's
is in
right.
juxtaposition to the one next to it.
That's right.
Within 1/1000th of the thickness.
Of a
That's
human
very precise.
It is.
Making a mirror out of segments like this is a brilliant solution, and it also reduces weight. Astonishingly, though the whole Keck mosaic mirror is 4 times as big as the Hale telescopes, it doesn't weigh any more. Theremin sensors allow Keck's mirrors to provide such clarity and resolution that they can distinguish each headlight on a car 800 kilometers away.
It's mesmerizing to look at the mirror itself because I guess most of us never see such a perfectly made thing. And quite expensive, I imagine.
Well, when they were built, roughly speaking, about $1 million each, we treat them as the most precious things we have.
But a perfectly aligned mirror isn't all it takes to see amazing images from space. The glass itself needs to be perfectly polished, and not just a quick rub down with a cloth. No. This is polishing on an incredibly small scale. Think of literally polishing atom by atom, and you're getting close. So how on earth do you achieve it with something like this? A sandblaster. To see galaxies billions of trillions of miles away, the Keck Observatory first needs to collect vast quantities of light. The huge mirror does just that. But to see tiny details of distant and dim galaxies, Keck's mega mirror also needs to be perfectly smooth. Just one tiny irregularity will distort any images and defeat the whole point of the exercise. Cue our next connection, which takes us back to 1871, just after the American Civil War.
Benjamin Chew Tillman has been a general in the Union Army. Legend has it that Tillman sees patterns etched onto windows by sand blown by the desert winds. Whether or not that's true, Tillman did invent a machine that blasts small particles at high speed.
Today, Tillman's machine is found wherever you want to strip rust or paint or dirt. It's a sandblaster. To see how it scours paint from an automobile wing, I visit the workshop of Hawaii's Mr. Sandman, Bob Freeman.
So this is where it happens.
This is our sandblast room.
That looks like the business end of it.
This is the sandblast nozzle. The abrasive is leaving this nozzle at supersonic speed.
Supersonic?
Right. Directed at the surface, and the particles coming out of the nozzle will take off whatever coating is on the thing that you're sandblasting.
Okay. So I just point that at the thing.
Hold this. I suggest putting it like this because it kicks back a little bit.
Right.
This is called a dead man control.
Dead man?
They call it a dead man because if you pass out or you trip, it'll shut off so you don't get hit with the blast.
I don't want to do it now. I'm blasting that, not me.
Well, that's up to you. You're going to be holding the nozzle.
Okay, so I hold that
So you
to
hold
tell
this.
it I'm not dead.
This is a safety button. You press that in, press that down, and be ready for it to start.
Right, well, this is the business end. I need this. Okay, and I blast. Here we go, sandblasting commence. Ooh, crikey. Oh, wow, look at that.
You know, I can get used to this. It's quite therapeutic. They might have to drag me away from it.
It works. Well, of course it works. It's been working since Tillman invented it. But it's all well and good for car parts and the like. But when you want to do finer work, even sand isn't fine enough. You need to go to another level entirely, an atomic level.
You can't polish a mirror with a sandblaster. It wouldn't make it anywhere near smooth enough. For a perfectly smooth mirror, you need to fire particles that are millions of times smaller than sand at it. But how? 100 years after Tillman invents the sandblaster, optical technicians construct a blaster which fires individual atoms. Without it, Keck's mirrors wouldn't produce sharply focused images. Now the technology is also used to dissect individual cancer cells. Sharpshooter Dr. Andy Bushby shows how it works.
So this is it, isn't it? Whoa, that's your atomic blaster. What do you actually call this thing for real?
This is a dual beam environmental scanning electron microscope.
Wow. Dual beam, you see, I'm loving that. But microscope, that's just for looking at things. I want to sandblast things at an atomic level.
Well, we can do that. Because this is a dual beam microscope, we have an electron beam that comes down here that we use to look at the sample. And over here we've got an ion beam which we use to cut away the sample with great precision.
Ions are electrically charged atoms. They can cut stuff atom by atom. Andy wants to show me how.
Exactly.
In the interests of science, one of my hairs volunteers as a guinea pig. Ow! We glue a bit of it to a plate. Even a tiny hair would shrivel inside the vacuum in the atom blaster. To make it hard, we freeze it in liquid nitrogen at minus 195 degrees Celsius.
So into the liquid really fast.
Into the liquid really fast. That's now freezing my hair.
Okay, so we're going to do a cryotransfer. We're going to take your hair from here over onto the microscope.
Cryotransfer? Yeah. Do I have to do this quickly?
That's all right.
I'm quite nervous. So that T-bar at the top goes on there, yeah? So I just push that in, yeah?
That's right.
A microscopic coating of platinum helps target the ion beam.
Right, so then I just push this, do I?
Finally, my hair goes into the atom blaster itself.
That's it. Yep, you're onto the stage.
That's my hair.
That's one of your hairs. Yes, that's where you've glued it down. Here's some glue. And there's your little hair sitting across there.
So how close can we go with this thing?
Oh, we can get in there and look a little more closely. And we'll see the size of your hair. And we can come down and look at one of these flakes.
So that filling the screen now is one of the hairs off my head.
Why don't we write your name on it?
That'd be ridiculous.
Yeah, we can do that before your very eyes.
On a hair?
On a hair. Here we go. Now, the ion beam is delivering about 23 million atoms a second into a spot that's about 50 atoms across.
And you can see it starting to arrive.
This picture has been magnified 5,000 times. The eye in Richard is about 1,000 atoms wide.
So it really is working the same way as sandblasting then. It's just dozens and, well, millions of these things pounding in.
On a very small scale.
It's a lot smaller, yeah, it's a lot fiddlier, I'll grant it. Because that's my name, I mean, barely noticeable across the width of one hair.
One of your hairs.
And how do you use that then for polishing?
Well, here we're coming down vertically onto the surface so that we blast away a pattern on the surface. If we wanted to polish something very smooth, then we'd fire those irons in at a very low angle to the surface so that they just knock away eye spots on the surface and leave something that's very, very smooth.
So this process that can etch my name lost in the width of a hair, you're saying is heavy duty. And if you want to have some real finesse and polish, you send it in at a more acute angle rather than perpendicular. This is your heavy engineering going.
It's heavy engineering, but a very, very small scale, atom by atom.
And with such a perfect mirror, you won't be surprised to learn that Keck's engineers want to keep it spotless.
The Keck mirror is a very special piece of equipment. But like any mirror, once in a while, it needs cleaning. So let's go clean it. Obviously, it being the Keck mirror, you don't just walk up to it with a duster and clean it. No, there's slightly more to it. It's got to be very, very clean indeed.
Almost every night, the mirror opens to the elements. Insects, moisture, or volcanic cinders can smear and scratch the huge glass.
So this is just a jet of CO2, and you're cleaning the mirror basically.
Correct. The snow is soft and it goes right from a solid to a gas. It doesn't go to the liquid, so it doesn't get the mirror wet.
What are you actually cleaning off? I mean, it hasn't got thumbprints on it.
The snow impacts the cinder and knocks the cinder off.
And the cinder is tiny bits of volcanic...
Correct. The cinder is really sharp, so it can remove the coating quite easily.
Technicians restore the mirror to perfection this way once a month. Thanks to Benjamin Tillman's high-speed abrasive blaster, optical engineers figure out how to fire a much finer beam of particles to polish glass perfectly. Keck's are the first telescope mirrors to be polished this way. It takes a week to polish each segment. That's 72 weeks for both the Keck mirrors. But even Keck's perfect twin mirrors can't see everything in the night sky. Vast swirling clouds of cosmic debris are completely impenetrable. So how does a Korean War spy plane help astronomers devise a new way of sensing? The Keck Observatory can see more of the cosmos than any other telescope on Earth. It can see an almost unlimited number of objects in the sky. Sheer power finds stars too dim to see with the naked eye. But vast galaxies also hide behind clouds of dust and gas. And to see them requires a new way of sensing. (1953), the Korean War. American commanders want to stop trains supplying the enemy North Korean lines. By day, the bombers can see their targets. But by night, it's a different story. They fly blind. Then comes a major breakthrough. Military engineers devise a way of literally seeing in the dark. they mount a revolutionary camera on a plane. It senses infrared radiation given off by hot objects, like locomotives. Targets are once again as clear as day. This new way of sensing in pitch blackness or through smoke and dust is called thermal imaging. Today, search and rescue teams also adopt the exact same technology. I want to put it to the test. And I come to the Honolulu Fire Department to do so. Captain Alan Carvalho shows me where they practice.
The thermal imaging helps us tremendously in a smoke-filled environment for us to locate victims, see obstacles that may be involved.
So it's a pretty essential tool for you, and I guess the difference is enormous.
Definitely, enormous difference between having a thermal imager and not having it when we're doing a search.
They're going to show me thermal imaging in action. First, I'm going to find a victim without thermal imaging. Meet Rescue Randy. I won't know where he is. I'm going to experience what firefighters routinely face in reality. Only it's usually a bit hotter for them.
I'm going to give you some equipment, some knee pads and gloves, and see if you can find Rescue Randy within 5 minutes.
I reckon I look like a firefighter already.
Look good. Getting there.
Yeah.
Almost part of my crew. Get some gloves on.
Thank you.
Good. Do you have any questions?
No.
No.
Good. That way?
Yes, that way. We'll go. Good luck.
Thank you.
You ready?
Yeah.
Okay. Shut off the lights, Dean.
Room number 13.
There you go.
A standard firefighter's torch doesn't make any difference in these conditions. Fire Chief Allen uses his own thermal imaging camera to monitor my progress.
Right. The drill is you feel your... Ow! The wall. I found the wall. There's a wall in here. I'm completely and utterly disorientated. Oh, yeah, yes. That's the... Yeah, I don't know what that is. Ah! Is this somebody who needs my help? No, it's a thing. You can stay there. Well, I'm using all of my senses. Mostly, it must be said, touch and sight. And they're not helping. I need another sense. Was that the way I came in?
I don't even make it out of the first room by the time the 5 minutes are up. Rescue Randy would have been toast. Now I'm going to try again, this time with the thermal imaging camera. First, the officers place Randy in the sun, so he'll warm nicely. He'll emit plenty of infrared, which will show up on the thermal imager.
Now we're going to let you use our thermal imager, and you let me know how well it goes, okay? So here it is. We've rearranged the room. We have our same safety personnel set up in there. I want you to go and scan the room, see if you can find Rescue Randy a little quicker this time, okay?
It's just so disorientating.
Yeah, see how well this works for you.
Thank you. Lights out. That's a dark again. It's not got any brighter. Right. Okay, well, before I do anything, armed with my camera, I'm going to scan around the room. Oh, no, that's a safety person there. Hello, safety person. I didn't know there were people everywhere watching me.
Even furniture emits infrared radiation and shows up clearly.
Straight away. No, there's nobody else. There's no victim in here. So I can move through, feeling my way, as before, into the other room, which is here.
Right. Scan. Nobody there. Nope. Ah! There. That took a fraction of the time. There's no crawling around the walls to find by touch. This gave me another sense. A thermal sense.
The exact same technology that helps American pilots to pinpoint North Korean locomotives on the blackest of nights now allows firefighters to see through smoke. And 55 years later, thermal imaging also shows astronomers objects trillions of miles away, hidden behind cosmic dust. Keck's thermal imaging is so sensitive, it can detect a candle flame on the moon. And it can sense the infrared radiation from remote galaxies other observatories only dream about. But there is still one more problem for the Keck designers, caused by a star much closer to Earth.
Every day, that particular star that we call the Sun does its work to warm Hawaii and turn it into a tropical paradise.
And every night, as the sun sets, paradise cools down. Daily warming and cooling is hell for astronomers because their instruments expand and contract, which distorts the images. So what's the solution got to do with 19th century Florida and a killer lurking in its steamy swamps? Even on the icy summit of Mauna Kea, the tropical sun can raise the temperature well above freezing during the day. Keck's mirrors would expand and contract with the daily warming and cooling. The tiniest changes to the mirror would distort the images. Engineers need to find a way to stop it warming and cooling. And that brings us neatly to our final connection. Rewind to the 1840s. Florida's swamps are home to a formidable predator. Not that, but this. The mosquito. It carries deadly yellow fever. Physician John Gorrie notices that the lethal disease erupts mostly in summer. So he wrongly assumes warm temperatures are directly to blame. He sets out to make this machine to cool rooms using a simple principle. When a gas expands, it cools down, chilling everything around it, as Dr. Chris Hill, who knows all about thermodynamics, reveals.
This is a can of ordinary deodorant, which is a gas under pressure. Go ahead and spray it on your finger and tell me what you feel.
What are you trying to tell me? Okay, right, so just spray it.
It's like that. What does it feel like?
Cold, actually.
It's colder because the gas is expanding from a high-pressure system to a low-pressure system. It has to move the air out of the way in the volume that it's expanding into. This effort of pushing the air out of the way costs some energy. That energy comes from itself, which is its own temperature.
Right, so I'd have thought instinctively that it's cold because it's like a breeze, it's blowing past your finger. But what you're saying is then that it's under pressure in there. When it comes out, it's moving because it's expanding. And the effort of pushing the air out of the way is costing energy. And that energy has to come from its own heat.
Yeah.
So it's not the breeze, it's when it hits my finger, it is actually colder.
It is colder.
It smells lovely.
The cooling effect of expanding gas leads John Gorrie to the invention of the refrigerator and ultimately transforms astronomy. When a gas expands, it cools. A big can of compressed gas produces dramatic cooling.
Okay, what we have here is a normal mattress. Feel it, it's nice and soft and malleable.
Well, you'd expect it to be, it's a mattress.
Now let's see what happens if we fill it up with a can of compressed CO2.
Thank you.
Good.
Safety stuff. Okay. Gloves.
Thank you.
So I'll just lay this out on the table, yeah? And then we just blow it up.
That's right.
Okay. Let me guess, I'm doing the filling.
Yes, you are.
Yeah, thought of that.
Here you go.
Right. So this is just a cylinder of compressed gas. It's just a giant version of the... So
Big,
can we
deodorant.
Okay, I'll kind of test it. Right, so that's just gas coming out. It's just expanding.
Expanding gas.
Okay. Nozzle in hole. Well, it's inflating. I can see that already, but it would. The gas is expanding out of the cylinder into there and occupying more space. Thus far, Chris, all you're proving is this is a great alternative to a foot pump.
Well, it's certainly easier.
Is it my imagination, or can I see frost forming on the top?
Yeah, the gas is cold because it's expanding. It's doing work by inflating the mattress, and therefore it's getting cold. And frost happens when things get cold.
Oh, I've burst it! But I haven't overfilled it or anything. It's frozen. It's completely frozen. This was... It's frozen. So that's the effect of expanding gas.
Expanding gas was cold. It made the rubber plastic become very brittle, and it broke.
So we froze it. So expanding gas, then, is the secret of refrigeration.
Yes.
And my mattress is ruined.
Gori doesn't cure yellow fever. That comes later when people realize the role mosquitoes play. But he does pioneer refrigeration, which revolutionizes our lives, and now plays a vital part in the front line of astronomy. To stop the Keck telescope from swelling and shrinking, the observatory's domes use refrigeration. Keeping the telescope at a constant temperature is a big ask. Each dome contains more than 20 million litres of air. It's replaced every 5 minutes. Giant refrigeration units run throughout the day, keeping the dome at nighttime temperatures. And it's all thanks to the cooling effect of expanding gas.
So inside these blue boxes, it's exactly the same as the back of your refrigerator at home, except a lot bigger and not full of fluff and old pencils. But the theory's exactly the same. Gas is expanding, heat is being exchanged, keeping it cool in here. It really is a creature of the night, and there's no chance of that thawing out in here.
Keck is transforming our vision of the cosmos and how it began. It sees almost to the edge of the universe, including this still unnamed galaxy 13 billion light years away.
Humans have been fascinated with the stars for, well, pretty much as long as there have been humans. The brightest ones were given names by the ancient Greeks and Arabs, and we still use some of those same names today. Now we can see a lot further than they could, but we're still wrestling with the same questions they were. How and when did the universe form? When will it end? Are we alone? Keck is giving us glimpses of the answers.
Keck is a genuine marvel of modern engineering. Deep in its DNA are some startling connections. A legendary ancient Greek death ray provides the secret of curving a mirror to focus light. The weird-sounding theremin enables astronomers to create a bigger mirror than ever before. A sandblaster shows how to make a surface smooth. A camera that guided bombers allows Keck to find hidden galaxies. And a refrigerator is the key to keeping the telescope in shape. It's simple, really, if you have the right connections.